14 male rats were randomly selected and sent to space. Upon their return, the red blood cell mass was determined. A different group of 14 rats was held in the same conditions except for the spaceflight, and their blood cell mass was determined. We have a mean and variance given in the flight group and a mean and variance given for the control group. Does the evidence suggest that we have difference between the groups? So as before, we made the comment that what matters in these problems with regards to left tail, right tail is the ordering. We talked about this in the proportion section of it because those were independent as well. Same thing here. The ordering will matter as to which one you subtract first with regards if you have a left tail, right tail test. If you have a two tail test, it doesn't matter which way you go, right? We talked about that before. In this case, the keyword is different, telling us we have a two tail test, so it doesn't matter which one goes first and which one goes second. Again, I'm subscripting CNF, control, and flight. You can keep the A and B, 1 and 2, doesn't really matter. How do I know this is a two-sample independent mean test? First off, I'm given means and variances. That's a pretty good giveaway. It's a mean test. How do I know it's two-sample rather than one sample? I have two groups of things that if I were to replicate this over again, I would get different numbers for each group. Again, this contrasts with a one-sample mean problem where if I repeated the experiment, I would get different numbers for one group, but the other thing I'm comparing it to, I would get the same number. So I just want to, again, even though it may sound like beating a dead horse, I want to make sure we understand that the difference there is that in a one sample mean test, if I were to do it again, I would get different numbers for one group. I'd get a different X bar, but I'm still comparing it to the same number no matter how many times I do it. In this case, if I were to do this again tomorrow, I would get a different mean for the flight group and a different mean for the control group. How different? Who knows? But they'd be different numbers, to be different rats. Okay. So that's how I know I have a two sample test. How do I know it's independent? Because there's no way to pair the rats. We could have easily had this as a dependent problem because we can clone rats. Had we said that we took 14 male rats, we cloned them, and we sent one of each, right? An original and a clone, right? One of them went to space, one of them stayed here, right? Now that's a dependent test because we have a pairing because you just pair with your clone. Right, so that's a dependent setup. But in this case, there's nothing that indicates that there's any cloning or any way to pair them. I just have 14 rats and 14 rats. It'd be like, you think about you in this class right now. If I just had all of y'all and I did something for half and something with half, how would y'all pair each other up? Like, some of you know each other, some of you don't. Some of you know multiple people. Like, how would you pair off, right? And that's this case here. We just have 14 rats in each group. There's no way to pair them. And so that's what makes this an independent test. Our sampling seems fine. There's nothing that jumps out. Again, how do I know that? Ask yourself the three questions. We've already mentioned this. Is there anything with the sampling that says we're not representative? Not that we can think of. We're trying to make sure that one group looks like the other group. Is there any response bias? Would anybody have lied, or would anybody not remembered a question? Well, we're just taking data and blood data from rats. There's not really a way for the rats to lie about their blood data, right? Or non-response bias, right? There's no like, well, we sent 100 rats up there, but 90 of them died and we only got 10 back. That'd be non-response bias. That'd be a problem because what happened to the rats that died? What was their blood like, right? And would that have told us something? But we don't have that scenario either. So again, ask yourself those three questions. All three seem fine. We've already covered we're independent. And the last one is we got to talk about, do we have normality in our sample statistic of interest? Again, why is it important? That's important because that's what allows us to go to our Z and our T tables. We have nothing that says the distribution of red blood cell mass is normal. We could have easily added that problem, right? Red blood cell mass is known to be normal. Boom, we add that sentence, we have normality, we're good to go. That sentence doesn't exist in there. There's nothing about symmetry, nothing about skewness, and so we just have to rely on sample size, which we don't have. We need each sample to be at least 30, but each sample is not at least 30. So we should be a little bit concerned about this. And of course, I have here in the notes, because I want to make sure that we're thinking about this, had the problem said, as I mentioned, had the problem said, red blood cell mass is known to be normally distributed, we're good to go. Red blood cell mass is known to be fairly symmetric. We're probably okay. Might have a small concern. 14's kind of still far away from 30, but if I had said at least red blood cell masses are known to be relatively symmetric, I'd say, well, we have that symmetry, and 14 isn't a lot, but it's probably close enough, right? Or it's getting close, right? If we had known red blood cell masses are, that data is very skewed, I'd be really concerned. I'd be like, this isn't even going to work at all, right? We're going to be really far off. So be thinking about that. I want to make sure that you can synthesize all that information that we've talked about. It's no different than what we had before. It's just now we have to check it for two different groups rather than one group. Then we come to step 3. The biggest thing I want to make sure you're thinking about here is our symbols. This is where you have to be careful, and if you try to rush through it, you will make mistakes. The formula here says S sub C squared. The subscript just tells me the group, but the squared tells me that this is a variance, which means I need to plug a variance into this. But when I plug a variance in, I get to remove the squared because the squared is part of the symbol for the variance. If I want to square a number, I have to square the standard deviation. I want to make sure we understand that. S is the sample standard deviation. So if I decide to square a number, I want to square the standard deviation. So if the problem gives me standard deviation, the formula says you need to square it. But if the problem gives you variance, it has already been squared. Don't square it again. This problem gave us variance, which means we don't need to square it. It's already been done for us. You need to be thinking about that. That's one of the biggest areas that people will mess up on these problems. If you can avoid that mistake, you've probably avoided over 50% of the mistakes that you can make. So that's why I plugged in 1.12 and 1.04. I did not square root them. I did not square them. We were given the variance as the formula as for variance. We plugged them in. If I see a problem with standard deviations, I need to plug that in for S, and then I need to square it. That's why I didn't square it, though, because it gave me variances. Well, then it's just plugging numbers in. And again, remember we talked about this. The order doesn't matter because it's a two-tailed test. The order would matter if it was a one-tailed test. If it's a one-tailed test, again, you need to look at the way you've written the alternative hypothesis, and whichever one you put on the left goes first. Okay, so if you do mu sub A less than mu sub B, that's when you do x bar sub A minus x bar sub B. If you put the B first on the left side, then you need to do B minus A, right? Just keep it straight. So that way you're making sure you end up on the right side. In this case, had we flipped it, this would be a negative, but we have a two-tailed test. It doesn't really matter because we're considering both sides. Had this been a negative 1.58, it would look the exact same when I come to the next slide and I draw out my rejection region. This is negative 2.16, this is positive 2.16. If I put positive 1.58 or negative 1.58, it doesn't matter. It doesn't matter which side I'm on because I'm considering both because I have a two-tailed test. So either way, we're somewhere in this middle white region, whether we did it control minus flight or flight minus control, whether we have positive 1.58 or negative 1.58. Doesn't matter because it's two-tailed test. That would matter in a one-tailed test. Okay. And again, I'm subscripting with my degrees of freedom. Both of my sample sizes are 14, so I don't have to choose the smaller one. Had I had 14 rats in one group and 12 in the other, then I would have said, oh, 12 is a smaller number, subtract that from one. That would give me 11 degrees of freedom. But in this case, they're the same number, so it's pretty straightforward. And then p-value, again, just as it's done before, make sure you know how to write the probability statement, right? We never put not equal to here. We always, for a two-tailed test, multiply by 2 and go the direction of the test statistic. So because this test statistic is positive, I go greater than. Had I flipped them, had we done it the other way and this was a negative test statistic, I just write that as less than or equal to. Right, go to Excel to find the p-value, and you should get that it is larger than our predetermined alpha of 0.05. And then we wrap it up just like always. Because our test statistic does not fall in the rejection region and our p-value is large, we fail to reject. So that means we cannot conclude the alternative. And again, this is the other tricky part, just making sure we write that alternative out in words that make sense from an English standpoint. What does the alternative say? The alternative is mu sub C not equal to mu sub F. What that is saying is that the true average red blood cell mass in millimeters of the control group rats is different from the flight rats. And so that's what I'm writing right here. There's not significant evidence to conclude that and again, I need to have a population word. I can say the true, red blood cell count, or I can say actual here. We can say all, as long as it's in there somewhere and it makes sense from an English standpoint, to conclude the flight animal's actual average. So again, what metric average? Actual average. Then what's the context? Flight animals' red blood cell mass differs from, and like we said before, you can kind of just put that of. The other group can kind of shortcut you. If you wanted to write it all out, that'd be fine. You could say differs from the control animal's actual average red blood cell mass rather than that of. And so there's one more example left for us. Again, as usual, this would be a good opportunity if you wanted to go ahead, work ahead and see if you can figure this problem out on your own. If not, again, no worries. Just something to think about, see maybe where you stand here. On this problem, you'll notice there's not really a fleshed out scenario. It's just, is mu1 more than mu2? Okay, so we kind of strip this down to bare bones. So when we check our sampling, there's really not much to look at here. Not much can go wrong given how little you were provided. But you see the data in a table there, rather than in the words. It shouldn't throw you off. It should be, really no different. Notice it says work without a calculator. Again, this is just the math should work out fairly simple for you. There are no decimals involved at all in this problem, until you get to the p-value, which you will need Excel for to find an exact p-value. Again, if you're using the table, all you can do is bound it. As we talked about previously, that t-table cannot find exact p-values. Only a graphing calculator or Excel could. How do I know this problem's independent? I really don't have any clue about if there are any dependencies in the problem because there's nothing given. But we're going to kind of rely on, as we've talked about before, unless you see an issue, it's probably okay. I have two different sample sizes. I know for dependent samples, I have to have the same sample size because, again, how do I work that problem? And make sure you understand, the big picture. How do you work these problems? A dependent means test. My first step is take all the values in column 1 and subtract them from all the values in column 2, right? Or vice versa. It doesn't really matter as long as you stay consistent in your problem, but you're taking one column and you're subtracting it from the other. If I have 25 values in one column and 12 in the other, 13 of them don't have anything to subtract from, right? So that's kind of a dead giveaway right there. Now, that does not mean, as you saw the last problem, that a problem with two groups in the same sample size means it's dependent. That could just be coincidence or it could be by design, but they don't have to have a pairing. It's one of those square rectangle things, right? All squares are rectangles, not all rectangles are squares. All dependent problems have to have the same sample size in both groups, but if you have the same sample size in both groups, that doesn't mean it's dependent. Right, so make sure you're thinking about that. We are, again, almost assuredly in a situation where we have independence here. There might be some dependence on some of the values, and we just don't know much, right? So just something to kind of think of, but we're probably okay. We set up our hypotheses as the problem states pretty clearly is mu1 more than mu2, so that's a greater than problem. Again, it is important which one comes first, right? If you put mu2 first, you have to go less than mu1, right? Because, the ordering of these things matters. So make sure you're keeping that in mind. Your assumptions, again, nothing to talk about sampling wise. Are the data independent? We already kind of fleshed through that idea. Probably okay, but just something to make sure we're thinking of. And then at the end, again, it's kind of a broken record here, but I just want to make sure that we're all on the same page, that we need our sample statistic of interest to be normally distributed. That's what allows us to use the Z and the T for critical values and for p-values. In this case, we're told our initial populations x1 and x2 are normally distributed. That means x bar 1 and x bar 2 are normally distributed, so we're good to go because we started off with both populations being normally distributed. And again, this is that gated approach. That's the first thing we check. So since that works, we're good. We don't care about sample size. Otherwise, we would have to check sample size next. Our test statistic, what degree of freedom are we going to use? Again, the simplistic formula that we're providing you is take the smaller sample size and then subtract that from 1. The smaller of the two sample sizes is 12. Subtract that from 1 and you get 11. Again, I can put x1 first and then x2 because I've written mu1 first and then mu2. Again, just the order here left to right English-wise has to match the order here. Plug in the values from there. As we talked about on the last problem, just be careful here with what you're plugging in. Notice in this problem, I was not given variances, I was given standard deviation. So what I'm going to have to do is I'm going to take that 6 and that 5, and I'm going to have to plug that in and then square it because I was given a standard deviation and the formula asked for variance. So again, just something to make sure that we're keeping straight there. That's an area of concern. And then I'll just work through the math. 6 squared is 36, 5 squared is 25. Square root of 4 is 2. And so our test statistic works out to a nice and even 3. And because we have a right-tailed test, we're going to take our entire significance level, throw it into the right side over there. Picture should look like this. We've got to find this critical value using our t-table, again, or graphing calculator or Excel. 11 degrees of freedom, that value would be 2.718. Then find the p-value, and this is where you for sure would need a calculator to find the exact p-value. Again, remember how to write the probability statement. I know I've been beating dead horses with that. Just make sure we can do that. Understand to get the definition of a p-value is what tells me how to write that out, so that's why that's important. Very small p-value, which makes sense because our test statistic 3 would fall over here in the rejection region, so it would have to be less than 0.01. And then we wrap up like usual. Because our test statistic falls in the rejection region, our p-value is less than alpha, we reject it all. That means we can conclude that the one mean is more than the other one.